Thanks for inviting me to this really cool venue. I love the topic about future of computing because to me this is the year of snarks. I'm really happy to see ZK everywhere around ETH Denver this time. And well, I'll get right into it. The way that I view the tech toolbox, and I would say the number one message that I want to get across to everyone doing smart contract development, decentralized app development, is that there's a big toolbox. I think people learned about consensus early in blockchains, and at the beginning of smart contract programming got used to using hash functions and commit and reveal kind of mechanisms. And now everyone is kind of acclimating to the idea of zero-knowledge proofs. And you might get the sense that zero-knowledge proofs do everything, and that's not the case. For some applications and privacy goals, you need to turn to something beyond zero-knowledge proofs. And really, there's only two alternatives, maybe a combination of them. There's multi-party computation and trusted hardware enclaves. If you think fully homomorphic encryption is a third alternative, really it's threshold fully homomorphic encryption, and that's a kind of multi-party computation. So really, these two are kind of covering everything. Zero-knowledge proofs are absolutely they're not overrated. They're just it's the appropriate level of attention for ZK this year, but I think it's really important to understand that there are some applications that you need something else for. So I'm trying to popularize this notion that goes beyond MEV. MEV is kind of a hot topic, but I want to try to convey that one way of thinking about MEV in an even broader space kind of sets the stage for the kind of applications that you can't just solve using zero-knowledge proofs. You need one of these other two techniques. So the example that I have in mind is an auction that hides even the losing bids. So you might think of an ordinary auction as something where everyone commits to their bids in advance. They put security deposits down so they get slashed if they walk away without revealing their bids. Maybe they do a zero-knowledge proof ahead of time that their bids are they have the money to back up the committed bid that they make, and then we'll all reveal them at the end of the auction. That's great. That solves the front-running problem in that auction. But the problem that approach doesn't solve is the residual bids problem. So if you reveal all of your bids at the end of an auction, everyone who didn't win the bid still has demand that's unmet for the auction, and they've revealed the price that they were willing to pay. So this is not covered by MEV because MEV, resistance, fair ordering, that sort of thing maybe fixes the issue with the auction, but it doesn't solve the problem that you're leaking more information through this kind of protocol than you strictly needed to. So if you really want the full flexibility to write smart contract programs that have full control over what's revealed, what's not revealed, full flexibility in the hands of the smart contract developers, the zero-knowledge proofs commit and reveal isn't enough. You need either multi-party computation or TEs. I think that there's still room to clarify this point a bit, so there's a couple of ways of thinking about it. This is the current one that I'll try out. You can tell me whether this gets any traction. The problem with zero-knowledge proofs is that you can't prove what you don't know about. Zero-knowledge proofs have a prover. The prover has to have the witness, the secret data that they're talking about. In a setting with an auction, there's no one prover who has all of the bids, and you don't want to elect one of them to collect all of the bids and make the zero-knowledge proofs. So you can't prove what you can't see. I like the way that Henry from Penumbra described it, which is that for multi-party applications, there's a global state you think of as being, there's a global confidential state. No one has access to that global state, and you want proofs about that global state, but there's no prover, so how are you going to make a proof about it? And you can turn to multi-party computation or TEEs for that. I'm not going to say a lot about the credit networks idea, but I'll just give you a tiny flavor of it, and I'll try to convey that this is a cool idea that you would need the powerful zero-knowledge beyond just proofs to be able to do. So I think many people have seen Web of Trust in some form or another. This is like a classic concept, but it's not been tried in zero-knowledge yet. So my version of a Web of Trust is that the edges in this graph represent a willingness to accept counterparty risk. If I trust you for $20, I'm willing to let you rip me off for $20 even if I can't do anything about it. You're not supposed to mix money with friends, because if I borrow $20 and then default, our broken friendship is going to be worth more loss than the $20 was ever worth it, so it's not worth the risk. Even as a borrower, let alone the lender, it's not worth the risk. But that doesn't have to be the case if this credit graph were all in zero-knowledge. So in the zero-knowledge version of this, if someone defaults, you don't even learn that they defaulted. I'm not going to even go further into that to try to like convince you that this is a good idea. I just want to leave you with the idea that maybe some applications you've thought of before or that don't quite work in the plain text setting, when you switch to this, you can do anything in zero knowledge and you have full control over what's private and what's revealed. Maybe you can reveal even less information in an application than you would have thought of. Maybe there's some different approaches there. So I'd love to talk more about this later, but I'm actually just going to go in to try to give a couple of like technical details about how I view the TE-based approach to smart contracts. I won't go into super low-level detail, but I'll try to pick out a couple of levels of detail. So at a very high level, you're used to Ethereum. In Ethereum, all the transactions go on-chain. Everyone can see the transaction data. That's how the Ethereum transactions work. In a TE, a trusted hardware-based smart contract system, the validator nodes who are running the blockchain, they only see encrypted transactions. So the enclaves have a way of computing on encrypted data without revealing it to anyone else. And when you send a transaction, you're sending an encrypted transaction that only the nodes with these trusted hardware environments can execute on. Now, nothing on the blockchain is public by default. The enclaves can output public data if they want to, but they don't have to. And you know, by default have this kind of privacy flexibility. So this is the very high-level view. Everything goes inside the enclave, so it's private. Let's zoom in into just one more low level of detail, but it's not too complicated. How do you communicate with these trusted hardware enclaves? Well, the idea is that the trusted hardware enclaves generate a secret key, which they keep only within the hardware enclaves. You can think of this, if this is a network, the simplest idea is that all the enclaves in the network all have a copy of the same secret key, but it never leaves the hardware isolation environment. There's a public key for that secret key, though, and that's a public key. It's public. So if you're a user, you want to send a transaction, you encrypt just with ordinary public key encryption to the public key that all the enclaves have, and that's how the enclaves can compute on your transaction and, you know, upload the Merkle root of the next state to the blockchain, whatever. That's how you communicate to them. Users would also get information back from the enclaves by the enclave can output data encrypted to the user's address as a public encryption key. You use it for digital signatures, but you can use your address as a public encryption key too. All right, let's zoom in on one more detail that's you know, really important. Replay attacks are a big issue with TE-based systems. So this is where the TEs and the blockchain play really nicely together. What you want is that the transactions are assigned an order by the blockchain mechanism, and the enclaves should only compute on the transactions in the order that they appear on chain. So you can think of this as the enclaves should basically contain within the hardware environment a light client for whatever blockchain is applying the ordering of transactions. We'll have some things to publish like in about a week or so from now that kind of make this point a little bit more clear, but just for now, I think replay attacks are important, and having the blockchain together with the TE acting as a client for the blockchain is a way of ensuring that. Let's talk about one more detail, which is how do you upgrade software? Because everyone's blockchain has to upgrade, right? Upgrades aren't easy in a plain text blockchain. It does not get easier in a TE-based blockchain. Now you have to migrate state from old enclaves to new enclaves. There's basically two ways to doing this. One is based on an interactive exchange. This is where the old enclaves and the new enclaves are both online at the same time. The old enclaves check that the new enclave satisfies some policy, whether it's approved by validators, approved by code signers, or some combination thereof. And then they do an exchange process. The new enclave generates a key pair with a public key sent to the old enclave. The old enclave encrypts that consensus key to the new enclave so it can decrypt it. Now the new enclaves have access to the key material that let them keep operating on the old contract state. Another way of doing this is through the use of sealed files, and there's a catcher here. All right, there's a pitfall. So one option is called MR Enclave. This is SGX specific, but you know it's a general idea, which says that you can write something to a file, and then only the same processor and the exact same enclave program that wrote that file can read that file. There's another option which some existing systems use for now but are moving away from kind of gradually, which is that it's called MR Signer, and it says only the same CPU, but any program signed by the developers, like code signed by the developers, can access the file that was written by the original enclave. This is a super bad pitfall because it means whoever have the developer keys can just read all of the secrets that the enclave has access to, so it's very bad. Let's zoom in on one other aspect of this, which is that the Enclave is like, I mean, I didn't give any background, so I'm sorry about this. You'll have to just ask me for the sake of time for it. But Intel SGX is the example of a TEE that supports this kind of the interfaces that I've described so far. But that's just within the processor, right? That's just one part of your system. You've got a network card, you've got RAM, you've got a printer, I don't know, whatever else you have. All of that's outside the hardware enclave, so there's like a boundary between the trusted environment, that's the enclave, and the untrusted environment, which is everything else. And you know that smart contracts have access to storage, right? They use like a key value store that the contracts can access. That means that's interaction from the hardware enclave to the storage. So if you have a smart contract, this is like your favorite ERC20 token transaction. There's a key value record for all of the account balances. Well, the first thing that the enclave has to do is say, well, give me the encrypted storage value corresponding to this address. The key is encrypted, so you don't know which address is, and it returns a value. So that's encrypted, and only the enclave can decrypt it. That's cool. And then same thing for setting the account. Now, what's the issue with this? Well, this is going to reveal to this storage system which value it is that you're accessing. So this is traceable, right? Even though the key is encrypted, the key is going to be the same time every time the same user's balance is accessed. So roughly there is, I've used this phrase, an ORAM-sized hole in some of the first ways that you see implementations of TE systems. It's not just about the storage interface, but that's one of them. It's even just about the memory. The enclave only has so much memory on the Intel chip. They've got mega big caches, whatever, but you still need external RAM for that. And what the untrusted OS can do is actually interrupt the enclave after every single instruction and unpage all of the pages of memory. And then the untrusted OS gets to see a log of which pieces in memory the enclave is accessing. So that's access pattern leakage that you might not think of if you just think it's in the enclave, everything's secure. There's other attacks that involve an interposer. This is like a game genie for your trusted hardware enclaves. It like sits in between your motherboard and your RAM, and you hook up a logic analyzer to it, and maybe even like an injection thing to that. So that's like a very risky thing for the threat model. There's ways of getting around this by basically using ORAM absolutely everywhere to be really safe, but we don't yet, I think, understand all the implications of doing design around that. I have no track of where my time usage is, but we're behind anyway, so I wrap up here. It's taken me a long time to kind of accept that it's even worth working in the kind of building systems around TEE space, but I now accept it. It's like the only good way to go about doing this. But it does not mean that the TEE solves all of your problems. It really just means it creates a whole lot more extra problems for you if you want the benefits that it has. It takes extra care to make them secure. It's not a replacement for all of these other techniques. It's really something that kind of needs to be used in combination with all of them. And yeah, I'm going to leave it at that. So thank you.
In the context of MEV extraction, what if the block time is faster than you dumping, let's say, breaking the enclave?
I didn't follow. You're saying breaking the enclave and the block time?
Let's say that I use SGX, for example, to have...
You have to say it again with the...
So let's say I use SGX to achieve pre-trade privacy in my system to avoid MEV. What if the block time is faster, let's say, than how fast I can dump and decrypt the enclave's memory, etc.?
Maybe you would have to have something stretched across different blocks. Yeah, I mean, there's nothing that says that you have to have the enclave go exactly one enclave operation, within the span of one block. Maybe it has to be kind of an asynchronous thing or a roll-up kind of thing with the execution environment. That's one possibility. So yeah, it's not easy, but it's possible to address those kind of issues.
Thank you very much. This was super interesting. This is kind of a broad question, but based on kind of the current research directions, would you say that they are more along the lines of, we need to build enclaves that are more secure in practice at a base level, or, as you were saying, kind of layering these different approaches together to say that maybe we can mitigate the risk of enclave breaks that we read about increasingly in news? I guess, where is research going right now, and I guess to what extent do you think it's possible to mitigate risks of kind of base enclave attacks with
That's
these
a great
other
question.
techniques?
I think there's a huge gap between where the research direction is going right now and where I think it needs to go. I think the research direction right now, we're at this like peak negative sentiment, like what FTX did for blockchain crypto, SGX failures have done for the whole TE space.
Yeah, that's kind of what I had in
so
my mind.
there's not enough research, I think, going on to how to do these software-based mitigations around it, but I actually absolutely think it's possible, and at least software can move as fast as the ETH community can do developing of new things. The hardware side, I understand very, very little about, so I don't have a good sense of really what the challenges are to do that. My sense is that SGX design has set the bar so low that there should be room for some market competition, but that's a tall order to make something as fast as an Intel chip and easy to program, and that also does the Enclave bit. So I do think that there's a lot of research going on in that direction that's over my head, but I'm trying to learn about it, and I think that there's a big need and a good path for software mitigations building around this, and I think that's slowly increasing, but I mean the time to build all of that is when it's at this peak negative sentiment. So yeah.
Cool, thank you.